TunePocket.com. 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 TunePocket.com.
So I welcome in 7th lecture of MAT-501. So in 6th lecture, that is lecture number 6, we define first characteristic function. What is the definition of characteristic function? See, if capital A is subset of R is a set of real numbers, then characteristic function of A, so it is denoted by chi of A, chi to suffix A, and it is defined as, so chi of A of x, chi A of x, it is 1 if x is element of A, and it is 0 if x is not element of A. So this is basic definition of characteristic function. So after that we write two notes, that is characteristic function of empty set is always 0. If A equal to B, then their characteristic functions will be same. So here it should be B. It's okay. There are some editing or erasing problems, already we have seen it. And second, if x a equal to xb, sorry, that is chi a equal to chi b, then these two sets should be same. So in that case, a should be equal to b. See, after that we have seen some properties of characteristic function. So first property, chi of a union b equal to maximum of chi of a and chi of b. Second property, chi of a intersection b equal to minimum of chi of a and chi of b. Third property, chi of a minus b equal to chi of a minus chi of b. Fourth property, chi of a complement. So a dash means a complement. It is equal to 1 minus chi of a. Fifth property, chi of u equal to 1, where u is an universal set. And last property, that is chi of empty set equal to 0, or chi of phi is 0. So after that we proved first property, that is chi of a union b equal to maximum of chi of a and chi of b. So how we prove this? So for that we consider two cases. Case 1, if x is element of a union b, then obviously chi of a union b will be 1. Chi of a union b of x will be 1. As x is element of a union b, so that should imply x is either element of a or element of b. So it should imply that chi of a of x equal to 1 or chi of b of x equal to 1. So that should imply that what is maximum value of chi of a and chi of b? So one of them is 1. So if chi of x equal to 1 or chi of b of x equal to 1, so surely their maximum will be 1. Hence what we get, so it gives that, see, chi of A union B of X is 1 and maximum of chi of A and chi of B is again 1. So both values equal to 1. So that will imply, let us see. So what it gives that, that is chi of A union B of X will be equal to maximum of chi of X and chi of B. So it gives equality, so which we claim to prove. So similarly, we consider second case. What is second case? If X is not element of A union B, then what happens? Then chi of A union B of X will be 0 because X is not element of A union B. So in that case, chi of A union B of X will be 0. So now, if X is not element of A union B, so it implies that X is not element of A and X is also not element of B. See, so it should imply that chi of A of X equal to 0 and chi of B of X equal to 0. So it gives that maximum value of chi of A and chi of B will be 0. So, up to that, what we get? So it gives that, so their maximum value is 0 already. Chi of A union B of X equal to 0. So therefore this maximum and value of chi of A union B will be same. So you get equality. Hence, in both cases, we proved chi of A union B equal to maximum of chi of A and chi of B. So, what is our second property? Second property, that is, so up till this second property, proof of second property, we have seen in lecture number 6. So, in this lecture, we'll prove second property. What is second property? Chi of A intersection B equal to minimum of chi of A and chi of B. So again, in similar way, you can consider two cases. So either X is element of A intersection B or X is not element of X intersection B. So case 1, if X is element of A intersection B, then what happens? So obviously chi of A intersection B of X will be 1. But if X is element of A intersection B, so it gives that X is element of A and X is also element of B. See, so it is there. And what we get from X belongs to intersection B, so X is element of A and X is element of B. So it gives that chi of A of X equal to 1 and chi of B of X equal to 1. So both are equal to 1. So therefore their maximum value will be 1. So maximum of chi of A and chi of B will be 1. Already chi of A intersection B is 1. So you will get equality. When you get equality, if X is element of A intersection B, so what happens for second case? What is second case? If X is not element of A intersection B, see, then chi of A intersection B will be 0 because X is not element of A intersection B. Using definition of characteristic function, so you'll get chi of A intersection B equal to 0. If X is not element of A intersection B, so obviously that will imply X is not element of A and X is not element of B. So it gives that chi of A will be 0 and chi of B also 0, and therefore their minimum value will be 0. Means if X is not element of A intersection B, in that case you are getting minimum of chi of A and chi of B equal to 0. Already you get chi of A intersection B is 0 and therefore you will get equality. That is chi of A intersection B will be minimum of chi of A and chi of B. So in both cases we proved, see, in both cases we proved chi of A intersection B equal to minimum of chi of A and chi of B, and hence we will get a required equality, that is chi of A intersection B equal to minimum of chi of A and chi of B. So that was the proof of second property. So remaining properties, that is property number 3, 4, 5 and 6. So in similar way you can prove at home. So I'm giving it for homework. So do it at home. Properties, remaining properties means say 3, 4, 5 and 6. So next definition, that is definition of equivalence relation. See, what is the definition of equivalence relation? Just a minute. Yeah. See, next, what is the definition of equivalence? If A and B are two any non-empty sets, then set A and B are said to be equivalent sets if there exists one correspondence between A and B. So there should exist one correspondence between A and B. What is one correspondence? See, what is one correspondence? So one correspondence means, see, a function which is both one and onto is called one correspondence. So there should exist, see, one and onto mapping between A and B. So then we say that set A is equivalent to B and similarly B will be equivalent to A. See, so from that you can write these remarks. That is, remark first, every set A is equivalent to itself. Second, if A and B are equivalent, then B is equivalent to B. And third, what is third? See, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So actually, first remark, it is called reflexive property, reflexive definition of relation. Second, it is symmetric. And third, it will be transitive, or it is transitivity. Transitive relation or transitive property of a relation. See, so this is about equivalence relation. So next definition, sorry, it is equivalent sets. So next definition is countability or countable set. What is called countable set? This set capital A is said to be, see, the set capital A is said to be countable set. So when we say A is countable, just a minute. Yeah. When we say set A is countable, see, if A is equivalent to set of all positive integers, if set A is equivalent to set of all positive integers means set of natural numbers. If set A is equivalent to set of natural numbers or set of positive integers, then we say that set A is countable set. So this is the definition of countable set. What is meaning of countable set? Let us see. So when we say A is equivalent to set of positive integers, it means that. So what is the meaning of this? That is, so in short, you can write, see, that is, there exists one and onto mapping between set A and set of natural numbers. Let us see, or set of natural numbers to set A. So there should exist one and onto mapping. There is one correspondence between A and set of natural numbers. It means that. So if you consider set of natural numbers means it will be 1, 2, 3, and it goes to infinity. And what is set A? Suppose set A, it is A1, A2, A3, and it goes to infinity. It means there should be one correspondence between natural numbers and that set A. Means you should assign. See, what will be image of 1? So there is one correspondence between n and A, means you should assign, see, 1 to certain element of A, 2 to some element of A, 3 to some element of A. So there should exist, let us see, one correspondence between n and A, means you should give counting to elements of A. So this is first element. I'm taking image of 1. So 1 goes to, let us see. So 1 goes to A1, 2 goes to A2, 3 goes to A3, similarly 4 goes to A4, similarly 5 goes to A5, and it goes to, means you should count elements of A. So this is first element. What is the meaning of this? So this is first element, this is second element, this is third element, fourth element, fifth element, and so on. You should assign, you should determine the elements of A, which is the first element, which is the second element, which is the third element, and so on. Means that set will be countable. You should decide the first element, second element, third element, fourth element. So such a set will be countable set. So this is the definition of countable set. So you can observe equivalent meaning of countability. So actually, what is the definition of countable set? Set A is said to be countable set if A is equivalent to set of natural numbers or set of positive integers. See, so you can write this note. If a set A is not countable, then it is called uncountable set. So it will be definition of uncountable set. When we say set A is uncountable, if it is not countable, it is not countable means see. So there does not exist one-one correspondence between set of natural numbers and set A. Means you are not able to give counting to elements of A. Means you cannot determine which is the first element, which is the second element, which is the third element of that set. Means you cannot give counting to elements of A. So in that case, that set will be uncountable set. So you can consider one example of countable set. See, what is that? So show that this set of integers. Set of integers means, what is set of integers? Means that is said it contains all numbers of the type C 0, 1, 2, 3. It goes to infinity, plus infinity, and minus 1, minus 2, and it goes to minus infinity. See, so this is set of integers. Means it contains positive integers and negative integers, and 0 is there. So it contains positive integers, negative integers, and 0. Positive integers means set of natural numbers, and negative integers are there. So let us define a mapping F from set of natural numbers to set of integers. See, what is set of natural numbers? It just contains positive integers. See, so let us define a mapping from set of natural numbers to integers. How it is defined? So f of n is equal to n minus 1 divided by 2. When it is n minus 1 divided by 2, if n is odd integer, odd natural number, what is n? It is 1, 2, 3, it goes to infinity. If n is, means if we consider only odd natural numbers, then what will be their image? So their image will be, see, so if n is odd natural number, then their image is n minus 1 divided by 2. So you can observe. So what is the image of odd natural numbers? So image of 1 will be 1 minus 1 divided by 2, it will be 0. 3 minus 1 divided by 2, it will be 1. So see, 1 goes to 0, 3 goes to 1, 5 goes to 3, sorry, 5 goes to 5 minus 1 divided by 2, so 5 goes to 2, and similarly you can see. Means odd natural numbers goes to positive integers, and similarly you can observe even natural numbers goes to negative integers. So yeah, it is well defined mapping. You can observe this mapping is 1 1 and onto mapping, and therefore it will be 1 1 correspondence between set of natural numbers and set of integers. So it gives that set of natural numbers and set of integers will be equivalent sets, and therefore set of integers is a countable set. See, so it is one example. So there is one theorem, that is if a1, a2 up to an and it goes to infinity are countable sets, so then their countable union is again countable set. That is countable union of countable sets is again countable. So this is statement of this theorem. So we have to prove this countable union of countable sets is again countable, means you have to assign counting to this union. So for that, see how we'll flow this. So let us take suppose A1. So all these sets A1, A2, AN and all remaining. So these are countable sets. So you can count elements of each A1, A2 up to AN, A3. So that will imply, see, so capital A1 it contains A1 1, A2 1, A3 1. So I am taking suffix for first element, second element, third elements and likewise, and I am taking super suffix for it is element of A1. So A1 1, A2 1. So A2 1, this 1 stands for it is element of A1. Again this A1 1. So this 1 stands for it is element of A1. Similarly, what are the elements of A2? See, so I'm taking super suffix for element of A2. And this 1, 2, 3. So these are order of elements. So let us see. So in similar way we write AN. So A1 N, A2 N, and it goes to, so AN N it is nth element of capital N. A2 N it is second element of capital AN. So similarly you can write remaining. See, so what will be AN plus 1? So elements of n plus 1 will be like this, that is A1 n plus 1, super suffix n plus 1, it is first element of n plus 1. Similarly A2 n plus 1 and it goes up to AM n plus 1 and likewise. So there are, see, infinite number of countable sets. Actually what we have to prove? We have to prove their union is countable. Let us see. So next we define height of each element A, K, J. What is A, K, J? What is K and what is J? So here K varies from 1 to up to infinity and J also varies from 1 to up to infinity. See, so what is height of an element A, K, J? So we define it by J plus K. We are just adding suffix and super suffix. So addition of suffix and super suffix will be height of A, K, J. So what is height of? See, how many elements are there of height 2? So you can observe. So there is only one element, that is A1 1 of height 2. Similarly, how many elements are there of height 3? So you can observe, see. So there is only one element of height 2. There are two elements of height 3. See. So I should use different color. Yeah, it's okay. So there are two elements of height 3. Similarly, you can observe there are three elements of height 4. These are A31, A22, 2, and A13. See, similarly, you can see there are four elements of height 5 and so on. So from that, what you can observe, see, for m greater than equal to 2, there are m minus 1 element